With that out of the way, it is time to introduce our next speaker, Victor Ciura, a principal engineer at Cafion and a Microsoft Most Valuable Professional. When he's not pestering his colleagues about modern C++ style, Victor visits his alma mater, the University of Craiova, Romania, to give lectures to students. This time he'll be giving one here in Wrocław. This is Status Quo, presented by Victor Ciura.
Thank you. Hi everyone, welcome. First of all, I want to say I'm a bit of an awe. It's the first time I give a talk in a cinema, so that's impressive for me. So let's get started. We're going to talk today about Clang-tidy and AddressSanitizer, and specifically on Windows. So if you know and are familiar with some of these tools on Linux or other operating systems, this talk is focused just on Windows and how to leverage these tools on Windows. This talk is like a vignette in 4 parts. We're going to start by talking about tooling. Then we're going to see how we can deal with legacy code and how we can make it comply with the newest standards and find bugs and do code transformations at scale. We're going to talk about taking control and extending those tools further and building your own tools and building your own checks and your own transformations. And then we're going to see what the situation is in terms of available tooling in Visual Studio and how this IDE and toolset has progressed and what's the status quo in delivering those tools today and using them. So we're going to start with the tools. About 2 years ago, I did a talk at CPPCon introducing a new toolset, Clang Power Tools. It was like a case study, and we showed various things that we did and transformations that we did on our code base and bugs we found, and we introduced this new tool. For those of you who haven't heard about it, anybody heard about Clang Power Tools before today? A few hands, good. So for those who are new to this, it basically brings LLVM tooling like Clang format, Clang-tidy, Clang compiler to Visual Studio users. And that's all Visual Studio versions that are in use today. It's an open source project. It's on GitHub. You can contribute to it. Lots of people did. There is it under active development. There are plenty of issues and bug reports opened every day almost. We're try to keep on top of it. You can use it to just format your code in Visual Studio with Clang format, or you can use it by leveraging the static analyzer within, or you can perform code transformations at scale using the automation it provides. Talking about automation, under the hood it comes with a PowerShell script that you can use. It's highly configurable. It supports Clang compile and tidy workflows for reporting and automatic code transformations. It works directly with Visual Studio MS Build project types, so there's no need to round-trip information or to construct an intermediate JSON compilation database like the usual LLVM tools require you. So it does all the heavy lifting. It supports parallel compilation and constructs precompiled header files so we can speed up compilation under Clang. It automatically extracts all this information from the Visual Studio projects, and including preprocessor definitions, platform toolset, include directories, PCH information, and whatever other things are necessary. It's highly configurable. You can run it through the PowerShell command line interface, but usually what we found that best works for us and most of the users out there is using a configuration file, this Clang CPT config file, and there you can predefine all the parameters that you that are specific to your projects, and you can store this file in source control, you can share it with the team, and so on. Basic usage might look something like this. You can compile all the projects in a directory. You can ask to ignore particular projects or particular files. You can ask for particular checks that you want to run or transformations that you might require. So this is how a config file looks, for example. Most options are, most parameters there are optional. It does come with easy integration with all the CI/CD tools out there. We started using it with Jenkins a few years ago. Now we've moved to GitLab. It works in Azure Pipelines, in Azure DevOps. Basically, any DevOps or CI/CD tool that supports Windows and running PowerShell scripts. That's how easy it is to integrate in Jenkins, for example. Just write the appropriate command line parameters there, and you're off to go. And you can define hooks and rules on how to run it and when to run it. And you can configure where you deliver the reports depending on your CI/CD system, or either via mail or other messaging pipelines that you have internally in your enterprise. A developer workflow for this means a Visual Studio extension that we developed. You can easily find in the Visual Studio extension marketplace. This is how you would, I'm going to walk you through quickly through the configuration options and setup, and then we're going to walk through using it and see some of the stuff that you can do with it. So this is how you would use it just for Clang format. It comes right in the box. You can install directly from it side by side multiple LLVM versions, and you can experiment. For example, you might be on LLVM 8 right now, and you want to experiment with LLVM 9. This is what we're doing now, and we already found some issues in our code base on LLVM 9 that weren't there in the version 8. So you can run them side by side and experiment. You can provide additional parameters for the Clang compilation driver. That's Clang++, not Clang CL. So basically, you can pass the standard Clang compilation arguments there. You can set it up, and I recommend that you do so, in that it treats warnings as errors. An interesting workflow that works very nice for us is making it that each time you successfully compile with MSVC in Visual Studio, it does a background compile with Clang and reports additional warnings and or errors in Clang. So on each save or compile in MSVC, you can make it compile under Clang. This works pretty neat for our team. Clang-tidy comes with over 250 built-in checks and modernizers. You can play with them individually. I wouldn't recommend turning all of them on. So this is how you would select multiple checks to run with wildcards, or maybe you can specify your own check there. You can, if you're using Clang format in your team, doing Clang-tidy auto fixes and code transformations can end up messing your code formatting. So you do have the option to automatically run Clang format after each tidy auto fix, so the code looks the same on everybody's computer. You can even do tidy on save. This is an interesting workflow. We didn't think about this one. Actually, Jason Turner suggested this one, and he experimented with it, and it's an interesting way of using it. I'm still not used to this style. Handy toolbar in the IDE right there. You can invoke client fixes on a whole project or solution in the Solution Explorer. You can run it in contextual on a single source file or multiple source files. So basically, you can pick and choose your granularity and how you want to deal with it. You have the Clang compilation errors in the output window and the error window standard in the IDE. So it's navigatable. You can double click to go to the warning or the error, takes you to the right place, just as you would expect from the Visual Studio IDE. Soon we'll have even in-editor suggestions and squiggles. For the Clang-tidy static analysis report, you have that in the output window. This is not a terribly great experience because the output of the static analyzer is pretty verbose, and some coloring or navigation would be nice in this static analysis report. We still don't have that, but we're working on it. So this would be the status of what we have achieved in those 2 years and stuff we're working on for the next versions. So if you're looking for using it in CMake projects, that has been done already. We're working on the squiggles and file previews and better reports for the static analyzer. Okay, so why should you care about this? I told you about a set of tools, and what does it help you with? So it helps you with if you're working on a large code base or on a legacy code base, or even for a new project. If you want to make sure that you don't do any mistakes and follow best practices and find hidden bugs, you want to run with the highest warning levels possible. You want to be as pedantic as possible to find any corner case or undefined behavior that you might have in your code. And you want to modernize a legacy application and make sure you remove all the unnecessary old craft. And you want to do that at scale. You want to do this. You don't want to do this manually. You want to leverage tools to do this across your code base. And we did that in these last years. Our code base is fairly large, and we've been working on it for 15 years now, over 15 years now. And it did need this refreshment. So we're very happy with the results, and I'm hoping that you're going to be encouraged to do the same for your projects. So now we're going to focus on legacy code and stuff we uncovered. But first, a mandatory slide. Let's gauge the audience. Who's still stuck on an old C++ version? Just one hand, and ashamed of it. Okay, very good. How about C++ 11? Few more, like a third of the room, I think. 14? A bit less than that. 17? Not bad. Okay, so you need to spot C++ standard conformance issues, and the purpose of that being non-standard or non-conformant code might be hitting UB, or might hide some bugs. Think about narrowing conversions. Think about I don't know, overridden virtuals that were not intended, or think about a non-virtual destructor. And Visual Studio since 2017 does make a great leap in this direction of standard conformance, in that it provides, I don't know if you knew that, but it actually comes with 2 compilers for C++ in terms of front end. And to get the new standard conformant compiler, you have to pass this switch to the MSVC compiler or set it in the Visual Studio configuration property sheet. And this will ensure that, by the way, this is a breaking change. You will see weird stuff after you do this switch. This is now the default in Visual Studio for new projects, but you have to make the switch manually for your existing projects. So you will uncover plenty of stuff when you switch to permissive minus and use the standard conformant compiler. This is, by the way, the compiler that will bring the newest features in the C++ language. So the old legacy compiler is still around, but you won't get all the benefits from the new C++ whiz-bang features. So you will see stuff, but you will uncover problems even if you're dealing with older Windows SDKs. For example, if you're still targeting Windows XP or Windows 7, you will have to use older SDK versions, and those headers are not standard compliant. You will have to shim them or find workarounds. We had to deal with this stuff a little bit. So it's not all that pleasant. But if you're targeting modern operating Windows, recent versions of Windows, you might be better off. The latest STL from MSVC, everybody knows now it's open sourced. It's on GitHub. So you can check it out. You can make pull requests. The latest MSVC compiles with Clang 8 and actually requires it because they use fancy new features. Maybe soon they'll require Clang 9, who knows? Maybe in 6 months or so. And goals that you can set out for your team, for your projects. The same things we did and we're still working through. Experiment with Clang-tidy checks and static analysis. I do encourage you to do that. But a hurdle towards that direction is getting your code to fully compile with Clang using the correct VS project settings. And this is an iterative process. You don't have to turn it all the way up. You can adopt it gradually. You can suppress warnings. I'm going to show you later how you can do intermediate steps to get you there, because it's not all or nothing. You can take tiny baby steps. Of course, you're going to find compatibility issues between the two compilers, even in permissive mode, permissive minus mode. MSVC and Clang are very different compilers, and you're going to find lots of different things between them. Stuff compiles in one and not the other. It usually goes the way that it compiles under MSVC, but not under Clang. And even though you're using, and I do hope you are, using the highest warning levels on MSVC and treating all warnings as errors, like I show you here, even in that situation, you will find plenty of stuff to dig through. And mind you, there are not false positives. You might get false positives with static analysis, but there are no false positives with Clang warnings and Clang compilation errors. If you're just restricting yourselves to WAll and W extra or pedantic. So don't confuse this with turning everything on. There's a W everything Clang command line. Don't use that. That's experimental. So you're going to start fixing this code and finding bugs. It's a long process. In doing so, you're going to need to do some large-scale code transformations. Not everything can be done by hand. So you're going to leverage Clang-tidy as you're building a more conformant versions of your code base. At the same time, you're going to leverage tidy transformations to change some of the code. So it seems like a catch-21 kind of thing, but it works in parallel. One helps the other. So you will get a gradual adoption there. But the very first step I encourage you to take is actually switch to the new compiler by turning permissive minus on. Just a few examples. I'll walk you through a few examples. By the way, if you have questions during the session, do raise your hand. I hope I see you. The light back there is pretty bright, but I hope I see you. If we ran into timing issues, I'll ask you to defer the questions to the end, but feel free to interrupt me. I'll walk you through a few of the stuff we found, just some random examples I've picked. For example, delete non-virtual destructor. We've had plenty of those. Hiding overloaded virtual functions, hiding virtual functions by overloading them. For example, in this case, an extra parameter was added to a function that was not in its original version in the interface. For loop analysis might seem silly, but after several iterations, some loops ended up looking kind of weird. How many of you are working on older than 5-year code bases? Okay, so you understand what the pain. Okay, so when you iterate through code is not right once. Code lives, code is transformed, many people touch it. So when code evolves, weird things end up in there. So actually finding induction iterators or induction variables incremented in the for declaration and the loop body, it sounds stupid, but it happens. Pessimizing moves. When you get to C++11, you get all the hype and enthusiasm, and you start writing everything in lambdas and start moving everything, everything. That enthusiasm is not justified. Mistakes will be made. Luckily, there are checks to catch overly enthusiastic moves like that. So pessimizing moves when they're really not necessary, or when they might hinder optimizations by the compiler. For example, return value optimization. Doing a move that there might inhibit RVO. Lots of these offenders, like data members that were not in the right order in the class initializer list, corresponding to their declaration in the member body. So we had to fix plenty of those, and you do have to build automatic transformations for stuff like that if you want to do it at scale. Question there?
Is there an already existing implementation?
Wait for a mic. I can repeat the question.
Is there an already existing implementation for fixing W reorder? Somewhere in Clang-tidy or other projects?
Not that I know of. The time where we hit this issue, we're not hitting it right now. So we hit this issue 2 years ago. Since then, being the check on, we don't get this issue anymore. So 2 years ago, when we did it, there wasn't any check. So we built our own. And unfortunately, it looked so bad and so special purpose that we were ashamed to open source it. So might be at the moment, but I'm not sure. So do check it out. Also check Clang Query is a very good tool that helps you actually debug some of this stuff. So we built our own, and it wasn't that difficult, but it was not general purpose. We built it on the special cases that we encountered. So that's why we didn't bother open sourcing it.
Thank you.
But that's a very valid point. These come up a lot, and you need to fix them at scale. You cannot fix them by hand. It just takes too long. Missing field initializers. Another thing that we found frequently in large data structures with configuration parameters. Lots of field initializers were missing. Again, there's no fix to address this at scale. This is a little bit more tricky to build. So, yeah, community input is good here. Another frequent offender is two user-defined conversions, which is not allowed to be applied by the compiler. And we found plenty of those regarding strings and constructors, non-explicit constructors. For example, here, constructing a string locale fastset from a character array, and a constructor that takes const string reference. So this is a frequent offender in, at least in our code base, and I'm guessing in yours too, if you've been on MSVC for long. Delete non-virtual destructor. This was pretty common with shared pointer and unique pointer, and other special kind of resource management classes that we have internally. You store interfaces that don't have a virtual destructor in those. So this was, again, a very frequent thing for us. This interface didn't have a virtual destructor, and we stored it in a shared pointer here. Same thing with unique pointer. Plenty of instances of this thing. You'll be amazed what you're going to find in your code base if you run this. One thing that's really nasty is regular enums, the C++98 enums, not the new ones, where there were situations where the wrong enumeration was used, and it actually compiled. And in some cases, it actually worked because the underlying integer value was the same, although it semantically wasn't the same, the same identifier. In some instances, it happened to work because it was the same index in the enumeration, but we did find bugs where it was actually a different thing, and it wasn't covered by tests, and well, it was a bug waiting to happen. So this was like really scary. Unused private fields. You'd be surprised when a code base lives long enough and there's plenty of thrashing in your classes. You'll be surprised, especially if they're not very tightly designed and they become pretty large. You'll be surprised how much garbage is left over and stuff that your compiler is happy to leave there, even though it's unused. So you'll find references, pointers, and pods in your data structures that are unused, but are just sitting there. You won't be able to detect user-defined types that are stored if they have a constructor, because that might have a side effect. So you're not going to be able to detect those. And watch out for orphan method declarations as well, because the linker is happy to leave those in and not bother telling you about them if they're not used anywhere. So you'll have plenty of orphan method declarations as well in your headers. And those inhibit this warning, because if your class has an orphan method declaration in its header, then the Clang compiler assumes that you have a definition somewhere, and that definition might use those data members, and it won't warn you about those. So the first step is actually finding dead functions without body. I told you about the iterative process. You can go gradually. You can turn off some of the warnings, specific warnings. There are compatibility switches with the Microsoft compiler, even specific versions that you can target. There are flags that put the Clang compiler in compatibility mode, for example, in terms of its preprocessor, because the preprocessor in the two compilers works very differently. So there are flags. I listed some of them here, and plenty of warnings that you can basically just temporarily ignore. So this will allow you to make a gradual adoption towards that direction. So I told you have to fix issues in your code and deal with older Windows SDKs. Plenty of issues regarding two-phase name lookup for templates. You need to do the proper includes for your template inline code. Fix issues for the dependent types, a lot of type name typing. Do not assume STL headers include each other. So this you'll have to be very explicit when requesting STL headers. For COM programmers, you might need to do some forward declaration for the unknown interface before including any Windows SDK headers, especially for the older SDK versions. Yep. By default, permissive minus sets this strict strings option. If you're dealing with a third-party library or third-party code that you don't control, it might be a good idea to just suppress the strict strings checks in the permissive minus compiler. And if you do that, I'm hoping that you will reach a point where, like we did, where you handle all the errors, WAll, WExtra, pedantic even, we're on pedantic right now, and you get rid of all the Microsoft compatibility stuff that you initially start with. So hopefully you'll get close enough, but it's not required. Initial steps will be very far from that. Clang-tidy comes with plenty of checks. This is some of the built-in checks and transformations that we found useful. I won't go into details, just very few examples. Remove redundant sister function, but you do need to watch out for hacks like this one, where the calling code actually relied on the buffer being null terminated. I wouldn't say this is pretty code, but we did have it. There are some bugs related to the special constructor for specialization for make unique. And after you do use auto transformations, so it replaces all the declarations or iterators that you might have, it replaces them with auto. Then the code becomes much more easy to read and more compact. there might be some leftover type definitions, so you might have to delete those by hand. Again, for loop conversions, it can modernize your loops to use range for loops, but it might leave behind declarations of iterators that are above the loop and are not in the loop declaration. So might have to clean those by hand. Yeah, question? Unfortunately for iterators, there's not, because iterators are user-defined types and they do have constructors. And can you repeat it? The question was, does it automatically report the leftover declarations above the range for converted? So the answer is unfortunately no, because those iterators are user-defined types in terms of having a constructor, and basically you're just going to have to find those by hand. Oh, sorry. There are some issues with using auto transformation. It messes up function declarations, function pointer declarations with standard calls and other macros. Yeah, Windows. There are plenty of string-related checks, and as you might have guessed, there are plenty of string-related bugs. So I do encourage you to leverage them. I'm going to briefly mention string view and some of the gotchas related to string view. There is a Clang-tidy check, dangling pointer. This is a very old check, still works, and it detects patterns like binding a string view to a temporary string value that goes out of scope immediately. And the string view does not extend the lifetime of the temporary string. So these kind of things are very frequent with string view and span. If you're interested to learn more about span, I do have a session tomorrow morning in stage 1 about span and some of the pairs there. So a simple example with a temporary string. I know this is a very toyish example, but very similar things will happen in real life. Imagine a function returning a string or something like that. So in Clang, we've had this for a while now, I think over a year now, maybe a year and a half. The W lifetime check. This is in a paper called Lifetime Profile by Herb Sutter. And there is an experimental implementation in Clang for, I think, since Clang 7, if I'm correct. And it checks for situations like this one and gives you an error like SV was invalidated when temporary was destroyed on line A. The lifetime of the temporary string ends at this semicolon. And more recently, in Clang 10 or Clang trunk, we've basically promoted this experimental switch, and now it's diagnosed by default. The warning issued is this one, dangling GSL, because it relates to a CPP core guideline check. And it detects the very same pattern, and the warning is a little bit more polished now. Object backing the pointer will be destroyed at the end of the full expression, and the full expression ends again at this semicolon. So I'm hoping similar checks will come for span. My understanding is there's a PR or working progress on that, but at least for string we have this right now. If you want to learn more about the lifetime profile and how these checks are built into LLVM in the Clang compiler, I do encourage you to watch this excellent talk by Gabor and Matthias. I do have my slides. I'm hoping you're going to get the slides after the conference or maybe even sooner. I do have plenty of links that you might want to follow, or articles you might want to read about, and I do reference other talks, and I encourage you to watch them if you're interested. So this is a very interesting talk about the implementation details of the lifetime profile in Clang, Clang 10. Now, let's talk about taking control, and referencing the previous question on building checks. The obvious next phase is you want more checks. You can never have enough. So you want to build your own modernizers, doing your specific project code transformations, and you have to learn how to use that. It's not that difficult. I'm not gonna tell you that it's breezy, but it's not that difficult to build simpler checks. It's surprising sometimes. Checks are organized in modules. You can plug in at the preprocessor level in Clang-tidy with PP callbacks, or at the AST level with AST matchers. This is more frequent using AST matchers. Checks can report issues the same way the built-in checks do, and you can even supply fixits. This is the more interesting part that I encourage you to explore. You can actually program fixes for your specific project transformations that you want to run, but you need to understand the structure of the AST and the regularity of the structures and the patterns you're trying to uncover there. There are tools that come with the LLVM repository. There are Python scripts, for example, that automatically generate boilerplate code for you to get you started with a new check. You can use the Clang query tool I referenced earlier to do interactive prototyping with the AST matchers and explore the structure of the AST. The Clang query is a very nice tool to try to visualize the AST for the pattern you're trying to match and find the appropriate identifiers or declarations that you're targeting. And it's a rinse and repeat kind of process. You won't get it the first try, so you have to experiment with it and see how it works. Clang check, you can dump the AST to visualize it. The project structure for a very simple Clang-tidy check is fairly easy to navigate. This is boilerplate code that is generated by the Python script. You can get started by cloning the LLVM repository and using the tools section of the LLVM repository, and build the Clang check tools. I just left those as references for when you get the slides. So if we add let's say we add a simple check in the readability module. There are plenty of readability checks in Clang-tidy already, and we want to add another one. We call it prettyfunc. And this is what's generated for us by the Python script, 3 files. And the structure is very simple. Initially, we have to inherit from the generic Clang-tidy check. We called our check prettyfunction check. It resides in the appropriate namespaces. It has a predefined constructor, and basically 2 methods we're interested in: register matchers and check. Predefined signatures, you just have to provide an implementation. Register matchers registers a Clang AST matcher to filter out interesting source locations. This is where you target what you want to find in your code, in your AST. And check provides a function which is called when this match is found. So each time it finds a match, it will call that function. And you have to deal with it. Issue a warning or provide a fixit for it, and it will automatically be applied by Clang-tidy. If you want a preprocessor level analysis, sometimes you need it, but it's a little bit more complicated. There's a different callback. So let's register a matcher. We have to bind, we give it an identifier, let's say needle, and we have to bind it to function declarations. This is how we bind it to function declarations. And the check basically verifies that we have the registered matcher. And if, because we matched function declaration, if the function starts with get underscore, this is what we're targeting, then the diagnostics issued would be this string. This is the diagnostic we want to print out. And optionally, we can provide a fixit. And the fixit hint, you can provide a fixit hint, and if somebody invokes Clang-tidy without autofix, the fixit hint will be displayed in the output. You'll just see that suggested transformation in generated Clang-tidy code. if the user flips on the auto fix option, then the fix you provide here will be automatically applied and the source code modified. So here we provide a very trivial fix in that we replace any function that starts with get underscore to match our shiny new coding convention with uppercase letters. Okay, very simple fix. I just wanted to walk you through the mechanics and the anatomy of a very, very basic Clang-tidy check. Of course, you can do crazy, weird things, and it becomes more complicated. Question?
Do you think that this could be used for API migration?
The question, I can repeat the question. The question was if this can be used to do API migrations. Of course. Yeah. But for API migrations, if it's maybe a renamed API, it takes the same parameters, then it's just a simple replace. But if you have different arguments or in different order, then you'd have to do a Clang-tidy transformation. Yeah, and you can build one. Like I think I even saw an example of that in one of the talks I referenced in my next slide. I think. No, further along. There's a very nice talk by Fred Tingo at CPPCon this year. It's already on YouTube, and I think he shows an exact example of changing an API, internal API, but doesn't matter. This is how you would test your shiny new Clang-tidy check from the readability module. You just invoke it like any other built-in check. Of course, you have to compile your own version of Clang-tidy. I did mention that earlier. You can configure it. Clang-tidy checks can have input parameters where you can customize their behavior. Basically, you can throw anything in there. And you have a means of retrieving those runtime parameters during your code and change its behavior. For example, change how it sees or acts, or how it filters, or how aggressive it tries to be on matching stuff in your AST. I won't go into details. I just leave this as reference. There are ways to automate and build. This is how an AST matcher would look like if you dump it with Clang check. So you can dig through it and see the structure of your code you're targeting and see what you need to match inside. Clang Power Tools allows you to supply your own checks right there and specify your own version of Clang-tidy that you build internally. That's very easy. I suggest you run them regularly, and even for custom checks, but especially for the built-in ones that are very useful, I suggest you run them regularly. I mentioned earlier a few good talks. Refactor with Clang tooling by Stephen Kelly. This is a very, very in-depth talk and very interesting. Clang-based refactoring by Fred Tingo. This is the one I mentioned earlier. You should really look up that video on YouTube. A series of articles that I encourage you to read on if you're really interested in going into details, or you come up with issues when you develop your own checks. Okay, so now we're gonna get to the status quo in terms of what's available right now and the future of using LLVM tooling on Windows. So starting with version 16.2, Visual Studio 2019 has built-in Clang and LLVM support for MS Build projects, which is good news. It does come with Clang 8 as optional component that you need to check and install. And as opposed to Clang Power Tools that uses the standard GCC kind of driver, Clang++, this uses the Clang CL, which is a special driver that knows how to deal with Visual Studio specific command line switches, build switches, that is. You just have to select the appropriate components when you install or customize Visual Studio 2019. And there's a new platform toolset. On this giant screen, I think is readable. And you have to select Clang CL from the platform toolset when you want to build a specific project with that. So maybe you'll play around with flipping on this switch, building, flipping back to your own compiler, that is MSVC. It's a little tedious, but it's nice because it's in the box. The next release, which is in preview, version 16.4, I think it's the biggest release of Visual Studio 2019 up to date. It will bring a lot of interesting stuff. And among the goodies we have in 16.4 is built-in Clang-tidy code analysis. There's a very succinct blog article about this. I do encourage you to follow it, like 10-minute read. And again, you can turn it on. By the way, Visual Studio already came with built-in static analysis, the Microsoft code analysis, I think it's called. And now you can even switch on Clang-tidy from settings and enable Clang-tidy analysis. And it's very handy because it's right in Visual Studio. So just wait for the next release. 16.4 should be out by the end of this month, I think. And you get, just as with Clang Power Tools, you get warnings and errors in the error window, and it's navigatable and handy to reach out. You also get squiggles. So Clang-tidy analysis can run in background, and as you type your code or as you're reading your code, you might start to see some green squiggles pop up. Those are not the IntelliSense squiggles, but from Clang-tidy analysis that runs in the background. So I think this is nice. This is a very nice touch. We're trying to do the same for Clang Power Tools as well. Should come out soon. If you're not on the latest version of Visual Studio, this is in preview right now. I'm guessing you're not using it for production, but I do encourage you to play with it. There's really no problem. We still try to provide the same functionality for older Visual Studio versions. So if you're on 2015 or 17 or the earlier versions of 2019 and you are not able to move to the latest yet, Clang Power Tools will help you in this workflow. So there's a few minutes left. Let's talk about sanitizers and why they're important. There are a handful of sanitizers available. They started in the LLVM project at Google. We have the AddressSanitizer that detects addressability issues for memory. The leak sanitizer detects memory leaks, obviously. The thread sanitizers detects data races and thread interleaving issues. The memory sanitizer that detects uninitialized memory. That's frequent for C++ developers. We have a hardware-assisted ASAN and a UBSAN for undefined behavior detection. We're going to focus on the AddressSanitizer right now because, as it turns out, this is one of the most frequent problems in software nowadays. Still, over 70% of all CVEs reported are exploits due to memory safety issues. So this is the most important of all the sanitizers. The AddressSanitizers, or ASAN, is the de facto standard for detecting memory safety issues. There were tools before that, but this is the one that's most prevalently used today. And it's very fast. Its average slowdown is like 2x factor. And the memory consumption is a little bit higher, so you will have a higher watermark of usage for your application when you do instrumentation runs with the other sanitizers. So maybe 100 megabytes of extra memory consumed, but you don't ship that. So you just instrument it to find and run your tests and do fuzzing and find issues. So you're not going to ship it. And it's very usable because the performance impact is not as bad as other tools like Valgrind or something like that. It detects use after free, the dangling references, heap buffer overflows, stack buffer overflows, global overflows, use after return, initialization bugs, and memory leaks. It comes with two parts. There are parts in the compiler that are implemented, and there's a sanitizer runtime that actually instruments the application when it runs. So the compiler provides the instrumentation code and lays the stacks and the functions and generates metadata in the object file that will be consumed by the runtime when you instrument your application. And the runtime does hook several functions, the ones involved in memory allocation like malloc and free and memset or realloc and other functions. and it checks for poison memory. It sets up memory in certain way and shims those allocator functions, and then detects poisoned pointers and memory location that are accessed when they're not supposed to be. So it basically, as opposed to static analysis, this kind of analysis gives almost zero false positives. So it's always reports something meaningful, and that should draw your attention and try to understand and fix it, because it's usually means business. Great news, in the latest Visual Studio version 16.4, which is in preview right now, AddressSanitizer comes to Visual Studio. So for the first time, we'll have it on Windows, working in our favorite Windows environment. We've had AddressSanitizers in Clang for 7 years, I think, and in GCC for 3 or 4 years. And now we finally have it with MSVC as well, so I'm very happy with that. Can't wait to play with it. Again, comes with like an optional component that you need to install. You can play around with it right now. It's in preview. It's not perfect, so it's a beta release, but definitely you can play with it. It's workable. You have to enable it in settings for your project. So this is a per project setting that you need to enable, just as with static analysis. Unfortunately, at the moment, it's just for 32-bit applications. So they're working on the 64-bit ASAN runtime. So I'm hoping it will be not in 16.4, but maybe 16.4.1 or something. So I'm hoping for 64-bit support really, really soon. They're actively working on it. This is the payload you get with the runtime, depending on how you compile your project. Either it's a single exe project application, or whether it complies with dynamic runtime or static runtime. You will pull in the ASAN DLLs or static libraries that are required to instrument your code. So this is what it will be linked in your projects, in your DLLs and EXEs. An example of how you might break into some memory issues with ASAN. The standard ID exception handler, I think you all know this pop-up window. You've seen it before for runtime exceptions. And it will just report sanitizer errors here, heap buffer overflow. So it's a standard Visual Studio ID experience. It's not something new that you need to learn. So it's a very easy way to deal with it. And very localized. As opposed to Clang LLVM command line, you don't have to read that. As opposed to a huge dump that you would have to dig through yourself and find the appropriate place in your call stack and find the actual problem in memory, which will be here. As opposed to a CLI kind of experience, you get a much nicer IDE experience where you can even do snapshots and save those dumps for later. You can navigate and explore local stack variables. You can see the memory window, the standard Visual Studio debugger experience. I think the Visual Studio debugger is the best debugger in the world. I hope everybody agrees. I see just one hand. I'm not happy. So I do love this rich experience of using the Visual Studio debugger, and I like that I have all the power of ASAN from LLVM in a familiar experience for me, where I can dig through the memory window, I can see the state of my stack, I can navigate the call stack, and it comes with extra goodies if you're Azure inclined. Everybody seems to be these days. Everything is either in Azure or not worth mentioning, I see. So ASAN on Visual Studio comes with an Azure angle. There is a Microsoft Security Risk Detection Service in Azure that you can hook up with in. It will probably cost money, I don't know. But it's a nice thing to have if you want to scale up. ASAN works and only works if you have test suites, if you run your application, if you have enough coverage. So if you want proper AddressSanitizer reports and detections, you have to have plenty of test units, and you have to fuzz your inputs. And if you seed your fuzzing data and provide fuzzing data, you can leverage this at scale. If you want, you can go up to the cloud, or you can use your internal network to do so. You can throw a bunch of test suites and a fuzzing network that you can spin out many instances, either in the cloud or in your network, and just collect all those results and see where the failures occurred, and get all the sweetness, all those dumps that you can just pull in and open inside Visual Studio from other machines, and just visualize the call stack, the memory window, and just figure out where the problem occurred. So it's very nice because you can distribute it, but analyze it as at your own pace in your favorite environment. A very nice presentation about this. This was actually the initial announcement at CPPCon when Jim Radigan announced this. And you can see some really cool demos there. I do encourage you to watch that talk. There's never too many sanitizers. And I'm going to end on that note. You can write your Parmesan sanitizer, bipartisan sanitizer, or even some artisan sanitizers. And with that, I encourage you to actually roll your own and run them frequently. And thank you. That's it. We do have very few minutes left. If you want to ask some questions, I'll be more than happy to get some answers in on camera. If not, if you're too shy, you can definitely catch me on the hallways and ask me questions later. Thank you. Questions now? Yep, one here. Over here.
Yeah, basically I wanted to ask you about running the sanitizers, because when it comes to running the test, I mean, as you said, to have good results in sanitizers, you have to run the test. But then the decision would be like, do you run the test without sanitizers and also with sanitizers? Or you would run the test only with sanitizers, expecting that they don't change the behavior of the code?
I don't expect the sanitizer to change the behavior of the code, just the impact performance. If your tests usually take a long time, and that's a good problem to have, it means you have plenty of tests, maybe you should think about distributing them on many more machines. But if timing is an issue, then you might say, I don't want to run all the time with ASAN on, because it will take longer to complete. Or maybe you have, for example, we have pipelines that involve running all the tests before a build is marked as passed, or a branch can be promoted to go into testing and so forth. So a huge delay in that pipeline might not be fortunate, although might uncover things. So if timing is an issue for you, think about maybe doing overnight runs on ASAN and doing the daily, so the midday pipelines that occur regularly when things are pushed to branches and in your CI/CD frequent builds. Maybe don't do ASAN builds there and just do overnight ASAN builds. I don't know, whatever works for you. But I don't expect it to change the behavior of the
yeah, I was thinking more on not on the time is an issue, it's more on the ones that the time is an issue, and it's not an issue until you discover, like when you have like threading stuff, like some stuff that it's like a test fails, like flaky test that it flags because some timing
okay,
stuff.
so it's a test that's time sensitive itself because of threads and interleavings, and the performance impact might affect interleaving of threads. I would say that's a good thing, honestly, because you uncover other things in your test suite. Maybe the tests are not properly built. Maybe they make we actually had some tests that made assumptions about disk latency, and we discovered issues when running tests when we had high I/O throughput on some of the build machines, and we discovered tests that were failing, not because the test or the code was not properly done, but because they made assumptions about timeouts and throughputs on I/O, and we found very weird issues. So maybe it's an opportunity to build a better test or improve the test. But yeah, it might be frustrating at first.
Okay, thanks.
Yeah. Any other questions? Okay. If not, thank you very much, and I'll see you in the hallways.